Okay, so hello everyone, welcome to day number 19 of this series. And today we're gonna do one question, and we're gonna do this question, okay? So yeah, let's get straight into it. A car mass of 1200 kilograms accelerates from rest to a speed of 8 meters per second in a time of 2 seconds. Okay, so like let's write down the units that we know, right? So we know mass 1200 kilograms. We know the inertial velocity, which is 0 meter per second, and then we know the final velocity, which is 8 meters per second, and then we know the time. So that's a lot of units that we know, right? Okay, so yes, let's go to question number A. Calculate the forward driving force acting on the car while it accelerating. Assume that at low speeds all friction forces are negligible. So I have to calculate the acceleration and the force. So to calculate acceleration, right? We need to subtract inertial velocity, and we have to do v minus t and over t. V is 8, u is 0, so it's basically a over 2, which is 4 meter per second square. Alright, so I need to use this acceleration, and then I have to calculate the force using F equals to ma. So mass is 1200 kilograms, and the acceleration, which is 4. So you need to calculate that. So it's 4,800 newtons of force. So that's gonna be 4,800 newtons of force. Okay, so let's go to question number B. At high speeds, the resistive friction force F provided by the air on the body moving with velocity v is given by the equation F equals to vb squared, where b is a constant. Alright, so derive the base unit of the force that SI system. Okay, so the force here, right? The force here is force equals to this mass and acceleration. So force is Newton, mass is kilograms as an SI unit, right? And the acceleration is meter per second squared. So Newton will be equals to kilogram meter per second squared. kg meter per second squared. Wrong. The kilograms meter per second squared. So right here, this is the forward friction force. So F equals to F equals to dv squared. V is meter per second, and v squared. So it will be Newton equals to, we don't know what is b right now, and then meter per second square. So it will be meter square second square. So I need to get this from b, right? I need to get this as Newton. So I need to derive the equation for number b, which is, I think, it's question number 2. So this is question number 1. So this will be question number 2. Okay. So I'm going to derive the units of v. So to get Newton equals to kilograms meter per second square, b needs to be kilogram over meter. So to get Newton equals to kilogram meter per second square. I hope that makes sense. I don't know. I'm explaining this very bad. So it will be like this: kilogram meter multiplied by meter square second square. So this and this will cancel out, and we'll get Newton equals to kilogram meter per second square. It's gonna be the same, right? So P is kilogram per meter. So this should be P right here. So this should be the answer for question number 2, kilogram per meter. So kilogram per meter. This is kilogram meter per second square. So let's go to question number 3. I'll use a different color this time. Okay. So the car continues with the speed forward, driving force, and accelerates until it reaches a top speed of 50 meters per second. So car continues with the same force, and it accelerates until it reaches top speed of 50 meters per second. At this speed, the resistive force is given by the equation F equals to VV squared. Determine the value of P for the car. Okay. So the car keeps accelerating until it reaches top speed. So we already found acceleration right here, 1 meter per second square. So what we're doing is determine the value of P on the car. So the meaning of top speed right here is because like when a car moves forward. I'm sorry, my drawing is really bad. When the car moves forward, first understood. Alright. But let me redraw. My drawing skills are so good. So here's the car, right? It keeps going this way, and the faster the car goes, the more air resistance it's gonna have. So there's gonna be drag, more and more drag as the car goes faster and faster. So eventually the drag, the force right here, the air resistance force is gonna get big enough so that the car can't accelerate anymore. That means the car can give more force to overcome the acceleration, and that is top speed. It is where the car just stops accelerating. It doesn't slow down, it stops accelerating, and the speed that does happen is 50 meters per second. Right. So yes, so that means that at 50 meters per second, so it's 50 meters per second top speed, the forward force that we calculated, 4,800 Newton, is Newton forward this way. Then the drag and air resistance should have 4,800 Newton also. So it both cancels out, and there's no resultant force to create an acceleration. So I have to use the equation here to calculate the P. So F equals to PV squared. Force is 4,800 Newton. Velocity, which is the top speed, 50 meters per second. So if we plug all those values in, you will get the square. B will be 4,850 squared. So just use the calculator to solve that. 50 squared. Okay. So about B is about 1.92 kilogram over meter. So this is the value for number B. Let me back check real quick. 50 squared. Yes. So P is 1.92 kilogram per meter. Alright, so let's go to question number 4 or something, right? Yeah, it's 4. Okay, so I just calculated right here. Or should I go? I calculate right here. Alright, so sketch a graph showing how the value of F varies with value with V over a range of 0 to 50 meters per second. use your graph to describe what happens to the acceleration of the car during this time. So let's look at the formula here. So let's look at the formula. S equals to PV squared. B is a constant. Right? P is a constant. So and then P is a constant. It is a square root square graph. So what's gonna happen is let's draw a graph here. Okay. The force v squared. It's gonna be like a quadratic formula, right? It's gonna be like a quadratic formula where B is gonna be here, so about like that. Or something, yeah, like that. No, not like that. I forgot how the graph works for a second. Like that or something, you know? We're gonna do this. But this is gonna be the graph. So the force as the force increases, but it doesn't increase this that much because the gradient, the tangent gradient, isn't that big compared to the gradient like right here or something. It's really the gradient is large. So the force gradually accelerates for faster and faster, and that as faster as v increases. So yes, that will be the graph for this. So yeah guys, so this will be this will be at the end of today. So yes, I'll see you guys tomorrow. Goodbye.